Today I'm going to talk about BitVM, which is a way to advance Bitcoin contracts. The motivation, first of all, we all know blockchains don't scale. Lightning also doesn't quite scale. Of course, it scales like Bitcoin by a factor of 10x or something, but unfortunately not far beyond that. And we are asking the question, can we scale Bitcoin to billions of users at all? And in an ideal world, we would have like 100x to 1000x higher throughput. We would have a free market of L2s, like consisting of ZK rollups, sidechains, second layer protocols like ZK coins and stuff like that. And that would enable both rapid innovation and also cheap experimentation. And all of these L2s could be interconnected via the Lightning network. That is like somehow how I would roughly envision an ideal world of scaling Bitcoin to billions of users. But unfortunately, we cannot do that because we don't have any bridges that would allow us to bridge BTC into any L2s. Of course, we can use it on Lightning, but ZK rollups, sidechains, ZK coins, and stuff like that, they all cannot use BTC currently without relying on some federation, on some multi-signature in the end. And BitVM is trying to solve that. BitVM is trying to enable bridges into other systems. And the overview is I'm going to talk about how to introduce state to Bitcoin scripts, to have stateful Bitcoin scripts. Next, I'm going to talk about the architecture of BitVM. And finally, I'm going to talk about how to enable bridges with the BitVM architecture. Bitcoin script. Bitcoin script, unfortunately, Satoshi disabled secretly all of the fun opcodes. Like he discovered a bug in opcat and then, or like in the implementation of opcat, and then he got kind of paranoid and disabled essentially all of the fun opcodes. And what he left us with is a very reduced version of Bitcoin script, and it's reduced to the bare minimum. And it looks like as if we cannot do anything really interesting with it beyond the basic stuff that we know, which is like signatures, multi-signatures, hash locks, and time locks. But there are some opcodes left, and they are actually enough to do all kinds of interesting stuff, as it turns out. Also, scripts can be up to 4 megabyte in size. So even if it's verbose, like even if we have to compose things out of very limited opcodes, in theory, we can express quite a few things within a theoretically 4 megabyte large script. And since it is so interesting to play with that stuff, somehow an unofficial community of Bitcoin script code golfers evolved. And I'm part of that, and part of that Bitcoin script code golfing, or as part of Bitcoin script code golfing, the ideas behind BitVM arose. In particular, stateful Bitcoin scripts, because currently Bitcoin script is completely stateless. So when you execute a Bitcoin script, its execution environment resets after every script. Like there is no native way to have, let's say, a value X that is the same in script 1 as it is in script 2. Bitcoin script doesn't really support that natively. However, we can hack around that, and the general idea behind it is if we could just sign a value somehow, if we could create a signature for a value, then that would be already enough to introduce stateful Bitcoin scripts. Because we could enforce the same value for X in script 1 and in script 2. And we can simply do that by checking the signature for the value X in both scripts. And when the person who claims what the value is, or like the person who determines the value, if they equivocate and sign two conflicting values for X, then we can punish them, because we can easily prove that here's a signature that signs 2 different values for the same variable X. And that is the general idea behind it. However, how can we sign a value in Bitcoin script? Because we don't have check signature from stack, and there is not really a native way in Bitcoin script to sign a value. However, there are Lamport signatures, and Lamport signatures, they are very simple. And since they are very simple and they require only hash functions, they are possible in Bitcoin script. Lamport signatures are a quite simple concept. It's just for every bit of the message, you have two different hashes, hash 0 and hash 1. And if you want to sign a 0 bit, you reveal the pre-image of hash 1. The pre-image of hash 0. And if you want to sign 1 bit, then you reveal the pre-image of hash 1. And just by revealing one of these two pre-images, you can create a signature. The main drawback is, of course, it's quite large, because for every bit in your message, you need to commit to 2 hashes, and to unlock it, you need to reveal one of the pre-images. So if you have like 32 bits, then you need 64 hashes and 32 pre-images to unlock it. But it's still possible, and we can just use it to sign stuff like a byte, a 4-byte value, or even a U160, so a 20-byte value. We can also sign a 20-byte value. That is still feasible in Bitcoin script, even though it's a bit clunky and it's large. It does enable signatures for values, and that's why Lamport signatures also enable stateful Bitcoin scripts. And that in itself is already quite big, because stateful Bitcoin scripts enable all kinds of interesting new features. Here's a little example of how that would look like in Bitcoin script. Like the unlocking script would be just some pre-image, and then in the first line it gets hashed, and then we duplicate it twice, or like we just duplicate it to have it 2 times, and then we compare it to the first hash, and then we compare it to the second hash, and then we check if it was equal to one of them, and we push the bit on the stack to which one it was equal. So either it was equal to hash 1 or it was equal to hash 0, and depending to what it was equal, after that script was executed, we either have 0 or we have 1 on the stack. So that is a way to, or like the most simple way to sign a simple 1-bit value. And if we want to have more bits, we can essentially just copy paste this script 160 times for a 160-bit value, for example. In general, please ask questions if I'm going too fast or so. I'm so deep into the weeds. I've been working on that stuff for like 3 months straight, and I'm very deep into the weeds, and I'm not quite sure if it makes sense what I'm saying. So if you have any question, just don't hesitate to ask. BitVM, the paradigm. I kind of overloaded the term BitVM. It is multiple things. It's like the paradigm, and it's also the actual implementation. And in the white paper that I published, I mostly described the paradigm. And here, for the introduction, I'm giving a high-level overview of the BitVM paradigm first. First of all, the BitVM tries to keep things off-chain. That is similar to Lightning, that you just have some kind of contract that allows you to use the chain as a court when you have a dispute. But most of the time, you will not have a dispute, and the fact that you have the court sets the incentives such that you probably will not have to use it. Just like in real life, like most people get along with each other because, or like most businesses get along with each other because they know if they cheat each other, then there will be some legal consequences, and that's why everyone complies with the rules that we set up. And in a very similar fashion, BitVM operates. It operates in a two-party setting. There's always a prover and a verifier. Unfortunately, we can hardly get around that. but we can make it better such that we can expand it to a multi-party setting, such that there's a single prover and n verifiers, and all of them can challenge the prover at once. So like they can play the challenge response game in parallel against the prover. And that has nice features, because if only a single verifier is honest, then the security guarantees hold. But I will talk about that later more. For now, we will just say the BitVM paradigm in its pure setting, or its most simple setting, it's always using the prover and verifier roles, and there's two parties. Yeah, in general, we are using optimistic computation. That means we are not trying to execute all of the computation on chain. We are doing quite the opposite. We are trying to minimize the amount of computation that we have to execute on chain. And we are doing that by by disproving a faulty result instead of computing a right result. That is much easier. Like the verifier just asks the prover for the end state, for the final state, for the result of the computation. And if that result is incorrect, then the verifier tries to find the most succinct way to disprove that incorrect result. And in general, that is much easier than the verifier computing the right result on chain. That is also kind of intuitive, because, for example, if I tell you, let's say 100 times 300 equals 7, then you can easily say that 7 cannot be right, because it is way too small. So without even computing the actual result, you can immediately tell the result that I just said, 7, must be wrong because it's way too small. And that is like in general, or like there are many such. Often in computation, it's much easier to disprove an incorrect result than it is to compute the correct result. Another example is for example square roots. Like to compute the square root of a number, you have to execute a quite complicated algorithm, relatively in comparison to multiplication, for example. And but proving or like verifying a result, like if you give me a square root, I just have to multiply it with itself to see if it's the correct result, which is much easier. That's another example of why, or like that's another example for the fact that verification is often much cheaper than execution. And yeah, we have developed a tiny domain-specific language that we call Tree++. That is kind of it's a language built upon Bitcoin script, and that enhances the capabilities of Bitcoin script. And now I'm going to give a short overview about what Tree++ is. Most of all, it's a templating language for script. Since script is so limited, we often have to copy paste a lot of things, and yeah, in general, it is very handy to be able to evaluate constant expressions, such that, for example, I can write something like 2 to the power of 5, or some binary number or something. That is the most basic thing that you can do. But you can also unroll loops, for example. If you have to do something 32 times or so, you can just write a simple loop that unrolls this template with particular parameters. You can compose functions, and composing function allows you to compose functions and compose them into bigger functions and bigger functions and bigger functions. And this way you can manage a lot of complexity in relatively simple compositions. And using this templating language, we implemented some basic opcodes that we call composite opcodes. And it's for example, bitwise XOR or bitwise shifts, multiplication, and it goes even to us implementing Blake 3. Some people wondered why do we implement Blake 3? There are already hash functions in Bitcoin script. Why do we re-implement something like Blake 3? The reason is that we don't have opcat. Like, we cannot concatenate bytes in Bitcoin script, and that means we cannot verify Merkle proofs, because for Merkle inclusion proofs you have to hash the path, and to hash the path you always have to concatenate two nodes with each other to then hash them to get the next node. And unfortunately that's not possible in Bitcoin script currently, since we do not have opcat or something similar. And that's why we had to implement our own hashing function, and then we can do it on like on the byte level. Yeah, we are representing large byte strings just like as single bytes on the stack. So 20 bytes would be 20 stack items, not a single stack item of 20 bytes, but like 20 single stack items. And this way, yeah, we can concatenate them, and then we can, yeah, do everything with them what we can think of, or what we are used to from like regular computers. And yeah, that's allowed us to implement highly complex stuff such as Blake 3 in the end. And this language 3++, we are using it to implement BitVM. Oh yeah, 3++, also, that's where the name comes from. It usually contains many tab trees. So it's more than just writing a single script. It's also a language to write like graphs of transactions, which have scripts that are connected with each other. And yeah, they're potentially large. For example, the Blake 3 script is quite large. It contains, of I think, about 100,000 opcodes or so. But yeah, they don't have to be large, but they are potentially large. Yeah, and we are using 3++ to implement BitVM. And here I'm talking about not BitVM the paradigm, I'm talking about BitVM, the actual virtual machine for Bitcoin, which is kind of similar to the Ethereum virtual machine, but it is way more limited. And it's like in Ethereum, they have designed the entire chain to support this sophisticated virtual machine. In Bitcoin, we totally don't have that. It's the exact opposite, actually. Bitcoin is dumbed down such that it doesn't support all these things. So what BitVM actually is a huge pile of tricks or a pile of hacks that hacks something like an EVM into Bitcoin without changing its consensus rules. Yeah, the main idea behind it is that 3++ is nice, but we don't want everyone to have to handcraft and hand optimize low-level Bitcoin scripts for every application that they do, because yeah, handcrafting these scripts is super. It's complex, and it's error-prone, and it's expensive. It's an expensive process. It takes a lot of time. So a much nicer idea would be to build a generic virtual machine, which has like a nice instruction set, and then people can just use some high-level language that compiles down to that instruction set, and like that compiles down to instructions of that set, and then they can use nice high-level languages such as Rust or something to write their applications, and we just have a single tab tree circuit that yeah, all the low-level devs can focus on, and we built this circuit only once, and then everybody can use it for any kind of application. And yeah, this VM, the circuits in particular, they are designed to succinctly disprove any faulty result of that virtual machine. That is also a cool thing, because in general, it's not easy to, like for general computation, it's not easy to structure it such that it's easy to disprove any faulty result. You usually have to craft the circuit such that it has very narrow positions, and in these narrow positions you can do queries, and then you can do like a binary search over these narrow positions. But if the circuit doesn't have these narrow positions, then it's very hard. And yeah, by building a generic VM, we have that problem only once, and then we solve it once for every application. And yeah, ideally we would have something like a RISC-V architecture, such yeah, that we can use existing tooling to compile down to our architecture. And that's exactly what we are doing. Here are like rough specs of what we are implementing currently. We are implementing the basic instruction set of RISC-V, the 32-bit instruction set, of course. And that can then act as a compile target for Clang, GCC, LLVM, and like all the things, all the compilers that you know and love. And you can use all of your existing C, C++, and Rust, and whatever libraries. And in particular, you can use existing Stark and Snark verifier libraries. And yeah, then just compile them to the VM and run them in the BitVM. A bit more detailed specs. The VM, as we build it currently, can run for 2 to the power of 32, so roughly 4 billion steps. It has 4 billion memory cells of 4 bytes each, which results in about 17 gigabytes of memory. In the worst case, you would have about 40 rounds of challenge and response. In the worst case, the court case would run for about half a year. Every party would have to submit one transaction per week, approximately. And yeah, then it would run for about half a year in the absolute worst case. In total, you would have to write about 150 kilobytes of script over that half of a year. And what's important to notice is that this worst case is heavily disincentivized. Like in general, you can align the incentives such that the loser will pay the winner's fees. And also, once you start the trial, it is already certain who will win and who will lose. So there is no incentive really for an attacker to start this trial, because they know in advance that they will lose and that they will pay the fees. I think there was a question. Yes, Fabian.
Yeah, I was I already thought of that because before you said that. So like how with like complex scripts, how do you actually verify that the worst case holds? Like that there cannot be a state or like the program can run to a state where you would need 41 rounds of challenge and response.
Oh, that is quite easy, because you just limit the trace size to like 4 billion, and if the program would run for more than 4 billion steps, then it's already wrong. That result would be wrong. You can just say the prover has lost if the program doesn't terminate within the 4 billion steps.
Okay, yeah, makes sense.
Yeah, and we think like for all practical purposes, the 4 billion steps will probably be way more than you need. Also, you can reset the VM off chain in a fashion similar to how Lightning channels work. So you can just when you agree on a particular computation, you can just reset the VM and just change the program, and then you can use it for something else. The only limitation here is that it has to fit in these 4 billion steps. Yeah, the worst case likely never happens in any real-world applications. The system would have to break that it would make sense for anyone to ever execute the worst case. And also, like as an honest participant, you're always happy if somebody opens a trial against you, even if you're innocent. Because yeah, you will profit from it. They will pay your fees, and they will pay like a little bounty on top of it. So if you're honest, you are happy if somebody challenges you for no reason. Here's a rough overview of how that transaction graph looks like. Unfortunately, I cannot really zoom in here. Oops. I tried to figure out how that works, but it doesn't really. You can have a high resolution version of the graph here at github.com/bitvm/bitvm/docs if you're interested. Just to give you a very rough overview, here the first part, or like there are 3 main parts of it. Here the first part is the trace, the second part is the instruction, and the third part is essentially the memory. And what you do here in the first part is you do a binary search over the trace of the VM. The trace means that at every step of the VM, you can merkleize the memory, and then you get a root of the Merkle root of the memory. Somebody asked a question. Ah, yeah, cool. Yeah.
Robin, you're muted right now.
Oh, sorry. I think Gloria just posted the version 1 of the graph. There is also a version 2. Then what I'm showing here is, yeah, I confused you, Gloria, sorry. Yeah, what I'm showing here is the version 2, and the version 1 is almost the same, but slightly different. Yeah, like the first part is binary search over the trace. The trace is essentially just a list of Merkle roots, and every Merkle root represents the memory after executing a particular step. So potentially for every step you have a Merkle root off-chain. On-chain you need at most log tracelen many Merkle roots. So if your trace has 4 billion steps, then you need at most 32 many trace roots that you have to commit to in the chain. And yeah, the process is actually quite simple. The prover, they commit to a particular state node, and then the verifier just responds with a single bit saying if they think the root was correct or incorrect. And then if it was correct, then the binary search continues in the lower half of the trace. If it was incorrect, the binary search continues in the upper half of the trace. And the interesting thing here is that they really just exchanged signatures for values. Like the prover signs 160 bits, the verifier signs 1 bit, then the prover signs again 160 bits, then the verifier 1 bit, and so on. Always 160, 1 bit, 160, 1 bit, 160, 1 bit, and so on until step 32. And after step 32, the prover has revealed 32 roots, and the verifier has revealed 32 bits. And these 32 bits, if you put them together in a 32-bit number, then interestingly, they represent exactly the index of the last correct root. That is just by how the verifier chooses the bits. They just choose the bits to be 0 or 1, depending if they think it's correct or incorrect. And that implies, just very implicitly, it's nowhere explicit in the scripts. It's completely implicit that when you put these bits all together and interpret them as a 32-bit number, then you get the index of the last correct state node. And that means that index plus 1 must be the first incorrect state node. And this is how you implicitly find out which, or like how the verifier defines what they think was the last correct state node. And once they have defined what the last correct state node is, they have automatically defined a faulty state transition, because they know a route for which they know correct route that is followed by an incorrect route. And that means they just have to prove that the instruction following from the correct state into the incorrect state, that this one single instruction was executed incorrectly. And that is a very important concept here, that we just have to execute a single instruction. We can run the VM for 1 billion, we can execute 1 billion instructions, but on-chain, to disprove a faulty result, we just have to disprove a single step. And yeah, the entire first part is just to find the faulty step. And then the second part is that the verifier, they have found it, and then they ask the prover to reveal that instruction that that they just showed. And then after they have revealed that instruction, the verifier can disprove it because something has to be wrong about it. And there cannot be many things wrong about it. The first branches here on the left, that would be that in general, in every instruction has like the form operand A, operation, operand B, result. So something like A plus B equals C, for example. That could be an operation. If you would use the add opcode, then the most simple thing you can think of, the most simple opcode you can think of is addition, and then you have just A plus B equals C. So, and what can happen here is that, first of all, they could have read the value A incorrectly. And this is proven by this path. Here, if you go this route here, the most left route, you disprove the value A. It means the prover has committed to an incorrect value A. It is not at the position where they claimed. Like they are saying at address A, there is value A, but the verifier knows exactly how the Merkle tree looks at the correct state. So they can say, no, that's incorrect. There is not value A at the address A. And this is how they prove it with this path. The second path is to disprove the second operand, that would be value B. And the third one is to disprove the result. That would be, the value C was written incorrectly into the memory. And the other branches, they are just like the fourth branch with like the little, do you even see my mouse? I think you don't see my mouse, right?
Yeah, we see it.
You can see it?
Yep.
Okay, yeah, here that fourth branch that allows you to disprove the program itself. So that would be the prover executed an incorrect instruction. At the current program counter, there is not that instruction that the prover just claimed. So essentially, here is the entire program encoded. And to change the program, we would just have to change this route here. Everything else can stay the same. Here is the only part where the actual program is committed to. Yeah, and here these other two branches, they are just to disprove the program counter. I know this is super complex, and I'm pretty sure my explanation didn't help that much. It's hard to wrap your head around this stuff. Yeah, Fabian?
Maybe can you take one step back for a moment and like just make it more clear how this exactly then gets like, or how this is then how the protocol works on the higher level. So I guess this is then a transaction, like there are funds locked in a 2 of 2.
Oh yeah. I haven't even talked about how to deal with the funds yet. Yeah, this is more just like how to walk through a faulty state transition.
If you're still getting to it, then it's fine. I just was interested right now.
Yeah. A simple way to do it would be just that the funds are locked in the same output as the entire graph is in. So then just like the party who wins will be able to take the output, and that would be like the most simple way to control funds with that graph. But there are more sophisticated ways to do it for the bridge later on. I feel like it would be just, maybe it's just too much to explain all the details of the BitVM graph here. I will go through the rest of the presentation, and then if we have time, we can go back to this one. Yeah, this is in general the bridge. Sorry, this is the graph, and now the question is, how do we apply that graph to build bridges into other systems? And the main idea here is, if the bridge is a bit clunky, it would be fine. We can build the bridge such that it is used very rarely and only for large amounts. For example, like a trivial, just a random number would be, you can use the bridge only for minimum 10 BTC. And it would also take you, I don't know, 3 months to peg out or something. And that would still be fine, because most end users can just use cross-chain swaps. As soon as we have some kind of guarantee that the XBTC, or whatever we call the asset on the sidechain, or on the side system, whatever we call that asset, as long as XBTC is guaranteed to be anchored into Bitcoin value, and as long as you have a guarantee that you will always get BTC if you want for your XBTC, then these XBTC have value. And once these XBTC have value, then you can easily picture that some market will arise of liquidity providers enabling cross-chain swaps between different chains. We already have that between Liquid, for example, Liquid and Lightning. I think just Aqua was a wallet that was just launched that is based on that idea that it's kind of easy to have a Lightning channel on a sidechain, on the Liquid sidechain, and then interact with the regular Lightning network just via atomic swaps that you as an end user just don't notice. And that is the rough idea. So if we just have some kind of secure bridge, even if it's slow and clunky, it would totally enable bridging BTC to other systems, and it would enable it in the end efficiently, because we can just use atomic swaps. The guarantees of the bridge. First of all, it's just a federation. But what's way better than what we have so far is that a single honest member suffices. Like if the federation contains at least a single honest member, then the bridge is secure. And secure means the bridge is safe and live. Safe means nobody can steal the deposit, and live means you cannot stop a valid peg out. And yeah, we can have large federations, which is very good, because it's the more federation members we have, the more likely it is that there is also a single, that there is at least one honest member. And another cool thing is that if you're an exchange or something, or whatever stakeholder that has a high stake in the side system, then you can become a member of the federation. And once you are a member, then it's trusted for yourself, because you can be that one honest member. And this way you don't have to trust anyone. Even if all the other members are malicious, you can guarantee safety and liveness. Here is a great diagram from our design department that just gives like a very rough overview of how we envision the bridge. And in principle, it's quite simple. It uses an ingenious idea of Burak. He is the creator of Arc, and he invented the idea of connector outputs. And connector outputs is something very simple. It's just the idea that you can connect two outputs by pre-signing a transaction for one of the outputs, spending both of outputs, and this way you can atomically connect them to each other. In concrete terms, this is a very simplified version of the peg in and peg out, but I'll try to explain now. Like Alice would peg in 100 BTC here, and she would create an output of 100 BTC that is an N of N multisig. And this is like the federation. All federation members have to pre-sign. And they would pre-sign here this blue transaction. And the interesting part here is like they give the 100 BTC just to the operator, which is also an interesting optimization that we came up with. You can just give it to the operator. I will explain later how you can peg out to any user, even though that money always goes to the operator. But the most important part here is the blue output. Yeah, the blue output pre-signs the entire transaction, and it uses sig hash all and also signs these two inputs. Like there are two inputs coming from the kickoff transaction of the operator, which will happen later. It didn't happen yet. Like at the point of peg-in, it didn't happen yet, but they will know how the kickoff transaction will look like, so they can already compute the outputs that it creates, and then they can use it to pre-sign this blue transaction here. And this kickoff transaction is built such that the operator puts in an input, and then there are two outputs. One is time-locked. It takes 6 months until you can spend it. And the other one is the so-called connector output. And you can spend it at any time. But the interesting part here is that once the operator publishes the kickoff transaction, it will take them 6 months until they can execute the blue transaction. And they will not be able to execute the blue transaction before 6 months. And they can only execute the blue transaction if they still have their connector output. If something happens to their connector output, then they won't be able to execute the blue transaction because the signature here commits to all of the outputs of the kickoff transaction. So if the connector output gets somehow spent by someone in some way, then the operator will not be able to touch the funds here. So what we are doing here now is we have the connector output, which is a very powerful primitive because we can use it in conjunction with the BitVM. Like these red boxes, they are BitVM setups, one BitVM setup for each verifier. So the prover, the operator of the bridge, has for every other member one BitVM setup, a separate BitVM setup. And it works such that if one of the verifiers wins their challenge against the operator, then they win an output that allows them to spend the connector output of the operator. So if the verifier wins, if any verifier wins their challenge against the operator, they win an output that allows them to spend the connector output of the operator, which guarantees that the operator cannot touch the funds. And the cool thing here is that all of these challenges can happen in parallel. So every verifier can attack the operator in parallel. And if only one of them succeeds, they can take the connector output, destroy the connector output. And this way they ensure that the operator cannot touch the funds. And this is like the rough idea how such a peg-out can work. There are a couple more levels of complexity to it. But in general, this is the rough overview of how it works. I can go into more detail, but I will finish the slides first. Limitations. What are the main limitations?
Robin?
Yep.
Gloria has a question or comment.
Oh, yeah, I haven't seen that, sorry.
Hey, Stefan here. Is it kind of like for Lightning, also the connector output would have a sizable output attached to it so that verifiers are incentivized to look for kind of cheating?
Yeah.
Or?
Yeah, you have to align the incentive such that the verifier makes a profit if they disprove the operator. So the operator will have a deposit.
Yeah, the minimum value that has to be in the connector output to make it worth their while.
Yeah.
Cool.
So would you publish the kickoff transaction first and have that bounty in there, and then you try to do the peg-in?
You would just publish that operator output. You would not publish the entire transaction, or at least you would not publish the signed transaction because, yeah, putting this kickoff transaction on chain is also like the signal from the operator, which means I just witnessed a valid peg out in the sidechain, and that's why I'm going to proceed now with the peg out.
Oh.
Does that make sense?
Okay, so it's like an unvault.
Yeah.
Okay.
It's also like the operator makes the claim that a valid peg out was initiated on the side system.
Okay.
And that's important that they make a claim, because once they make a claim that they commit to, then you can use that claim and disprove it in the BitVM if it's incorrect.
Mm-hmm.
Conceptually, who's the operator again? Like, what do they do?
The operator is just one member of the federation that is in charge of operating the bridge, and essentially of paying the people who want to peg out.
So each federation has a single operator, and then that operator is kind of checked by all the federation members.
Yes.
Okay, thanks.
And they can like kill them, and then the next party becomes the operator. Like if you win against the operator, if they cheated, then and there's an honest verifier, then the honest verifier will win, and then they can kill the operator's connector output and essentially remove them from the federation, and then just the next party becomes the operator. And you start from scratch with the same setup.
Okay, thanks.
I know it's highly complex, and there are many levels of many piles of hacks piled on top of each other. So don't hesitate to ask any questions. I know it's complex, and I would certainly not understand it from my explanation. But yeah, limitations of BitVM. First of all, yeah, there is lots of complexity. The scripts that we are building are complex. It's a complex process. It has complex assumptions about fees and all that stuff. So it is not a simple solution. It's a complex solution, definitely. Also, it's complex to balance the incentives. Loser has to pay the winner's fees and a bounty, but fees are not static, so it's not easy to measure that. Of course, if the incentives are balanced, the chain is not needed. However, that's potentially capital intensive because you kind of have to predict the highest possible fees, and you have to put up capital to be able to pay for the worst case. So that's the interesting thing. Like if you are able to pay for the worst case, then the worst case probably won't happen. But if you're not able to pay for the worst case, then there's an incentive to exploit that. So yeah, it's pretty much, it boils down to capital costs, like the cost of putting up the capital and waiting, or like being there if you would need it. That guarantees mostly that you don't need it at all. Whoops. Yeah, a very good thing here in comparison to other bridges, that like other people have been doing research on Bitcoin bridges, and they usually come up with solutions that require some kind of one-to-one collateral or even over-collateralization. Here in our model, we don't need that at all, because we have that nice connector output thing, which essentially guarantees that if an attacker cannot touch the funds. So there is no need to over-collateralize anything or so, because all you need is them paying the winner's fees, but they cannot touch the deposit. So there is no need to collateralize it. And there are some scalability issues, like you cannot scale to a federation of 1,000 people, because for every peg in, all of the end parties have to pre-sign n peg out transactions in the end. So there's a lot of pre-signing going on. It's way less than I originally anticipated. Originally, I thought every party has to pre-sign the entire BitVM setup of all other parties, but this is not the case. It can be still two-party setting. It totally works out. But that peg out transaction, like the blue transaction, if you remember, that has to be signed by all n parties, and you have to sign it n times, because you need the entire setup n times, because when you kill n malicious, or like n-1 malicious operators, you still need the single honest verifier to be able to keep the bridge running, and that's why you need the setup n times. And in general, a federation can censor peg-ins. That's an issue. Like since all of them have to co-sign, if one refuses to co-sign, then you cannot do more peg-ins. That is definitely an issue, but it's not as big of an issue as if they could censor peg-outs. centering peg in, nobody loses money, right? But in a peg, centering a peg out, that would be equal to stealing money. Summary and outlook. BitVM definitely enables much more complex Bitcoin contracts. The main use case that I see is a trust minimized bridge, or in general, trust minimized bridges to all kinds of systems. Maybe there are also other use cases, but since it is slow and expensive, it doesn't really fit many use cases, but it fits the bridge use case quite well. Yeah, it is practical, but it is clunky, as I said. It's very cool that it doesn't require any soft fork, so we can do more innovation without any activation drama. And hopefully our toy version will be ready this month. We have already implemented since, I don't know, 2-3 months already. And we got it to quite a sophisticated level. Just yesterday, we we executed all transactions for the first time down to the Merkle path. So like the entire graph from like the top to the bottom yesterday for the first time. And yeah, hopefully we will even have a reckless mainnet this year where people can already use some small real amounts and use it in the wild. Yeah, that's it. Do you have any questions?
Robin, that's great. Thanks for jumping on. I know folks will have some questions. I see Fabian's got his hand up. Maybe a quick question for myself first. The BitVM enables this federation and this peg in, peg out. Is there a name for this bridge? You just call it BitVM Bridge, or does it have its own name distinguished from BitVM itself?
I'm working on a paper together with Alexei, and he calls it Sentient Bridge or something. But okay. I haven't really come up with any name that really resonates strongly with me. So I'm open for suggestions.
TBD. All right, Fabian, yes. You had a question?
Yeah, you had like some examples of stuff that is implemented, and you mentioned Blake, which I've seen, but I've also seen somebody post something about a function SHA-256 implemented in BitVM. Is that something different, or I'm just curious because you didn't mention it in your presentation?
I think that's different. I think that was more like playing around with ideas. We were really serious about Blake 3. Like we have completely implemented it to the, like, it just works. And I think the SHA-256 version was more like theoretical. It's like, yeah, we do have the building blocks, but they haven't built it.
Okay, got it.
But maybe I'm wrong here. I hope I don't say it.
I have a kind of a question related to that. Like how much of, I guess it's kind of unclear to me what goes on chain. Like you were talking about using 100,000 opcodes to implement Blake 3. Yeah. Is that something that you have in your, like, is that part of the script of a transaction you publish on chain?
Yeah.
But practically, does that work if it, like, that's a non-standard size, right?
Is it?
100K? Oh, I guess it's witness discount.
Yeah.
But yeah, like what goes on?
5 KB bytes, so it should be standard.
Right. Okay. Never mind.
And maybe here to show it, it's really like the very last transaction. Only here, either in this or in that transaction, you would execute one round of Blake 3. So only in the very, very worst case that the malicious party knows they have lost, but they still keep doing it for half a year and keep posting like the worst answer that they can to really get here and like to really end up there, and then at the end they would have to execute one round of Blake 3.
And so this 40 rounds over 6 months, is that worst case as in the attacker waits until the last minute to do another. Okay.
Exactly. Yeah, that's like the attacker trying to maximize the length of the trial, the duration of the trial.
And is it, so do you have to put all of the, I guess, value up front?
Yeah.
Okay. So you could like run out of fees and
that's
not be worth it anymore.
Yeah, no, the fees are not that much of an issue. You can always have anchor outputs and then just use these.
But like if it's an expensive fee market,
yeah,
and it's expensive to publish a transaction to make a proof,
yeah,
then you might not bother.
Yeah. So the collateral must, like you have to calculate the collateral such that the loser pays the winner's transaction fees plus some bonus in the worst case.
Mm.
You have to estimate what the worst case fees might be, and then the collateral has to be high enough such that the loser pays the winner's fees plus a bounty.
Okay, interesting. I have I guess, so I don't want to, I'm like a little worried that this will sound rude, I guess. So you mentioned kind of this very rich universe of possibilities of like, you know, the infinite amount of things that you can do here. Is that kind of the goal, or something you're just trying to demonstrate and you're actually looking to deploy something a bit smaller, or?
Like we are really building these bridges, and then everybody can use them to bridge BTC into their system. Like some people want to use it for Ethereum, others want to use it for Bitcoin sidechains, like Sovereign found it interesting, or like Rootstock people found it interesting. Or in general, everybody who's building sidechains can use it. Everybody who's building ZK rollups, there's another company that is building ZK rollups on Bitcoin. They are very interested in using the bridge. And in general, we want to offer that primitive for other people to bridge BTC into their system.
Okay, so they could have side chains where they have whatever they want.
Yeah.
And it's, I see, interoperable. Okay.
And then you can have like all the, like you can have all kinds of clones. You can clone Ethereum, you can clone Zcash, you can clone Monero, whatever you want, and then just remove the shitcoin and replace it with BTC, and then have essentially every feature, every blockchain architecture that you want.
I see. Okay.
Like the grand vision.
Very cool. Very cool. Thank you. Did you want to go?
Yeah, so Stefan here. Two questions. I think they're related. One is like a few months ago after it came out, the only function available was, I think, checking if value was 0 or something. And then it was said it was going to take a long time to build all of the functionality, whereas it seems now that you've already built a lot of it out quite quickly. Like what happened that things evolved so quickly? And then also what's the link between G++ and the VM implementation? Because I didn't quite get that, but I'm thinking it might be related questions.
Okay. Yeah, like Super Testnet is not here like in the zero sync team. BitVM, or like this, what I'm presenting here, is built by the zero sync team, and Super Testnet was toying around with BitVM in general, and he built the first prototypes, but they were his goal was just to build something as soon as possible and give people something to play around with. What we are doing here is a more complex approach that is aiming for more real-world use cases, and it's essentially two different projects. So it's maybe we should just not overload the name BitVM too much. Maybe we need to find a official name for this project to distinguish it from other things that are also called BitVM.
Okay.
And the second thing, the difference between Tree++ and the BitVM is that Tree++ is like that domain-specific language built on top of Bitcoin script. Like it allows these things that I mentioned, like unrolling stuff, or here. It is essentially just a templating language for script. That's the main thing here. And we are using 3++ to implement BitVM.
Okay. So it wouldn't be like if you're writing one of these contracts, you would be using the BitVM implementation with the language you want to use, and you would
use Rust or something. You would use C++, Rust, or whatever high-level language you're used to, and then compile that down to the BitVM instruction set, and then
okay.
Yeah. So normal contract developers will not deal with 3++ at all, and they will not deal with low-level stuff. It's way more like Solidity in the end for the developer experience. All of that stuff here, 3++ is not Solidity-like. We will have another language that will probably be just some Rust dialect that will be the main language to then express programs to run them in BitVM. This is just a templating language on top of Bitcoin script.
Thank you.